All right, hello everyone, and welcome back to the fall 2025 edition of the Physics 8A live stream. It's been a hot minute since I've live streamed. Busy summer over here. Was relocating the studio and setting it up again. Not quite done with that, but should be done by the end of the month. So things will look a little bit better as we go, but can certainly live stream. So I'm going to do that. And as a reminder for those of you who don't know, because this is Physics 8A and you might not be familiar with this already, I live stream once a week. After I got some feedback last spring and decided that I would be live streaming once a week and changing up the format a little bit, so I'll talk about that. But the main goal of the live stream is to basically review every week the important topics of the week and the important formulas, and then see how you set up problems in physics. Just in general, learning how to set up problems is important. And that sometimes is done in discussion, and if it is, lucky you. But sometimes it's not, and that's kind of a bummer, because that is really how you become good at physics, is by watching someone that knows how to set up and solve problems teach you how to do so. So the goal is to learn how to set up problems, and the goal is to do problems that kind of bridge the gap, in the sense that this live stream is not a lecture, so you should still attend lecture and get notes there. It's more of a recap of a lecture, and then this live stream is not really a discussion either. It is kind of the in-between, where we're going to take what we learned from lecture, review it real quick, and then apply it. And hopefully that will help you then be a bit more comfortable, so that when you are in discussion, you kind of have an idea of where to start. And that's the biggest complaint that students have, that I hear all the time, is that you follow what's going on in lecture, you understand it, and you can reproduce it to a degree, but when faced with a physics problem, you don't know where to start rather, or what to write, which is absolutely normal. Happens to everybody when you learn physics. You gotta it's kind of a chicken and the egg problem. You have to be taught how to solve problems, and then you have to try and fail a bit, and then try some more, and eventually you get good at it. But that's the goal of the live stream. And this all came about because a lot of students I had previous years would complain that they wouldn't get much out of discussion, because the problems were either too hard, for them to attempt them, or maybe just not really relevant when it came to exams. So I wanted to address that, and started these live streamings back then. And I've changed the format a bit. I used to do 2 sessions a week, but the first one was really just lecturing, and did not get as many views at all overall as the practice problems, which makes sense. The lecture is kind of already taken care of. So I've kind of changed the format. I'm going to live stream once a week, and it's going to be a quick recap of the important topics, and then applying it to 2 or 3 practice problems that are good problems to kind of understand how to think through the topics of a chapter, and how to set up problems and solve them in physics. So that's it for the updates, I think. I mean, that's again where the live streaming came from, and I made a few changes to make it a bit more efficient for you guys. But keep sending me feedback. I always appreciate it. Helps me, make a better live stream for you. So feel free to do so. And feel free to check us out at slackademia.com. So we have courses, study guides, and master classes. The Physics 8A live stream is a course. It is a free course that you can enroll in, and it gives you access to the live streams. I also post the problems that we do, so that you can have a typed up version of those problems. And I also post the solutions to the homework. So send me the PDF of the homework assignment, and I will post the solutions to the problems within that free course. You don't need a credit card or anything. Just create an account and add the course, and it's free. And then if you want to get in touch, probably the best way for now is the Facebook page, facebook.com/myslackademia. You can also find the email to the website there, the email and the website there, if you want to email me instead of DMing me through Facebook. But DMing me is usually the fastest way if you need to ask me a question or communicate something to me. So, with all that said, um, Physics 8A is a tough class. Not trying to scare anyone. It's a tough class for a few reasons. When it comes to Lowhorn and Golightly, it's usually not because of the instructor. They're pretty fair game. They're straight shooters, and you can always find reasons to complain. But overall, they're pretty fair game. So they're not necessarily the reason why 8A is going to be hard. 8A is going to be hard because there's a lot of content. It goes very fast, and if you've never taken physics before, you might find it quite intimidating, or at least I wouldn't say off-putting, but it will catch you off guard a bit because physics works differently than other classes. So that's also the goal of live stream, is to address this, is that physics is a very different class than anything else you've taken in the life sciences. Memorization is necessary in physics. You have to memorize the formulas and the lecture notes because otherwise you have nothing. But memorization will never save you when it comes to solving problems. Contrary to OChem or everything else in life sciences, well, in those cases, memorization works pretty darn well, and then you should probably memorize. But in physics, that's not the case. So that's something to keep in mind, and we're going to see what that means when we solve problems. But again, the hard part of Physics 8A is the volume. It's the sheer volume of content and the speed at which you have to learn it, because it feels like it starts off slow, but by the end of September, once midterm 1 comes around, it speeds up because there's a lot to cover, and we're going to go a lot faster because at first we try to ease into it a little bit, but it gets the speed ramps up quite a bit after midterm 1. So keep that in mind. Don't get caught off guard. If you can do a little bit of physics every day, I know everybody laughs when I say that, but ideally an hour a day would be great. And that doesn't mean you have to do everything that you've ever learned, every day. You just do an hour a day. Some days you do lecture notes, some days you make a cheat sheet, some days you do problems, but you stay on top of it as the content accumulates, because like that you'll have a better chance of being able to understand it quicker and not forget previous content. So, macro view, Physics 8A is the story of mass, really. And it's going to be done mostly through mechanics. There's a little bit of thermal at the end, but it's really the story of mass, and we're trying to understand how objects move, why objects move, under what conditions they do or do not move, and things of the nature, and what happens to their motion if they maybe collide with each other, or hit a patch with friction as they're sliding, or if they're rolling and whatever. So it's the story of mass at large, and we have to start somewhere, and we're going to start with what's called kinematics. Now, kinematics is how objects move, but not why. Okay, why is Newton's laws, that comes later, but kinematics is just how objects move. And so we are going to want to keep track of 3 different quantities. There's going to be what we call position. Okay. And this week we're going to simply focus on kinematics in one direction. Now that could be the x direction or the y direction, okay? But we don't do footballs that are being thrown like this that move in 2 directions, horizontally and vertically. That's next week, that's projectile motion. So for now, we're just going to study motion that occurs in one direction. I'm going to draw stuff along the x-axis. And what we're going to say is that, we'll choose an origin somewhere, and x of t is going to be the position of the object in question. By the way, all the objects that we study up until midterm 2, and we'll talk about that when we get there, all the objects we study are going to be what are called point masses. Okay, so this thing here, I drew a little point. It is what's called a point mass. You could also think of it as, or you might hear it called rather the particle model. It's the same thing. The idea that is that it doesn't matter if you have a car, a train, an elephant, or a marble. we shrink everything to a point and we give it a mass. And mass is not going to matter this week or next week because kinematics are independent of mass. Mass comes into play with Newton's second law, and then, well, third law, we'll see how that, we'll talk about weight and mass there, but mass shows up once we start talking about Newton's second law, F naught equals ma. And of course it has an effect on acceleration. It's just that here, today, we're just going to talk about position, velocity, and acceleration without worrying about mass. But all the objects that we study are going to be points. They have no shape, no size, no front or back, top or bottom. They're just a mathematical point with mass. So we do not worry about the shape or the size of the objects that we're studying. And as we study their motion, we don't worry about that. Okay, so position x of t is going to tell me where I am on the x-axis. That's pretty natural. If I tell you that x of t is, I don't know, 7 meters, you know exactly where you are. And if it's a function of time and it changes and later it's 9 meters, then you also know where you are. So it's rather straightforward. Okay, so if x increases, the object moves along the positive x direction, which seems natural. If x decreases, the object moves along minus x. Okay, now with that in mind, we don't know just with the value of x here, if we say that it's 7 meters, we don't know if it's moving to the left or to the right. We just know where it is at that moment. But if I then know later on where it's at, then I can say if it's moved to the left or to the right. And usually to the right is the positive direction. That just tends to be because of math. But you could make any direction the x direction, right? You could make positive x to the left. You could make positive x down a hill. That's up to you to a degree. But the point is, if x increases, the object moves in the positive x direction. If it decreases, it moves in the negative x direction. Okay, so that's just position. Now position, it's nice. I mean, I do want to know where I am at any given time, but that's really not a lot of information, right? It could be right here, but am I moving left or right? Or maybe am I at rest at that moment? I don't know. And so we also need to incorporate something called velocity, okay? I'm going to draw a vector here. It's really a component of the velocity vector along the x-axis, but we are just moving in one direction. So that would be a particle that's moving at that moment to the right. Of course, I don't have to be moving to the right. I can be moving to the left, and then maybe it's going to look like this. And of course, I have to be able to distinguish the two because it's not the same thing to move to the right and to move to the left. They're different, okay? And so if Vx is positive, the object moves in the plus x direction. So let me actually make a little bit of room. We'll do this. Let's do this. Moves in the positive x direction, which in our case is to the right, but you could define it to be a different direction. And if Vx is negative, the object moves in the minus x direction. Okay? And so knowing that will tell me what is happening to the object at that moment. Does it move to the right? Does it move to the left? Or maybe does it move up or down, depending on which direction I'm considering. So position tells me where I am. Velocity tells me how fast my position changes. Okay, so I'm going to make a little note here, and we'll come back to this in a second, that Vx of t is how fast position changes, and mathematically, that is the rate of change of the position x, dx dt, also known as the derivative of x with respect to t, and you could call it x prime of t if you want, but x prime is usually not, we don't usually use the prime notation too much in physics. We like the dx dt notation more. For obvious reasons, once you do enough physics, it just lends itself really well to deriving things and establishing things in physics. But it's the same thing as x prime of t, if you're more comfortable with that notation. Okay, so that's position. Then there's velocity, that's how fast position changes. But velocity could also change. Velocity could increase or decrease. And how fast velocity increases or decreases is actually acceleration. So the third quantity that we want to keep track of is acceleration. Now acceleration, as I just said, is how fast velocity changes. So it's really the derivative of velocity with respect to time. It's dvx dt. And again, we'll come back to this. And so if we have a scenario like this, where the particle, let's say the particle is moving to the right, with a velocity vx of t at that moment. Well, is the velocity increasing or decreasing? I guess one thing to know if you're moving left or right, but are you moving to the right faster and faster at constant speed? Or are you moving to the right, but you're slowing down? Maybe you're coming to a stop. Okay, and then the same question in the other direction, to the left. And so let's assume that I have an acceleration here, ax of t, that points to the right as well. Okay. Now if ax and vx are in the same direction, then vx is going to increase. Okay. Now I say that there's not a, I should say this a little bit differently actually. So if vx and ax are in the same direction, if velocity and acceleration are in the same direction, the speed increases. Because if I'm moving to the left, it's not true that vx, the velocity, increases. Vx is going to decrease. It's going to become more and more negative. So the speed increases. Okay, acceleration to the right is going to increase vx of t to the right. Okay, and the reason is that this is the amount by which vx of t changes every instant. Okay, so if I have an acceleration of 3 meters per second square, that means that every second velocity increases by 3 meters per second. Okay, that's what acceleration represents. And so if this is the change in v of x at any given time, well, change to the right means vx is going to increase to the right, and so the speed is going to increase. Okay, now let's consider the case where the object is still moving to the right. Okay, so this is going to be vx of t, but now it's slowing down. Okay, so now you have ax of t. Okay, and so if ax points opposite vx, then the speed decreases. It's going to slow down. Okay, because at any given instant, this is the change in v, and so if the change is to the left, it's going to subtract off of vx of t, and the speed and the velocity is going to go down. Well, the speed is going to go down. The magnitude of velocity is going to go down. So you're going to slow down. And that's really important to keep in mind because you don't want to confuse acceleration and velocity. They're two different things, obviously. And the effect of acceleration on velocity is easy to forget. It's not an obvious one because it's that of a derivative having effect on the original function. And so, here, if again, if to the right is positive, then this is positive, so the derivative is positive, meaning that the function increases. Well, here the derivative is negative, meaning that the function is going to be decreasing. Now, it doesn't mean you can't still move to the right. I mean, you can still move to the right and have a decreasing speed, but, you have to be very clear what these quantities are and how they're related. Okay, so are there other scenarios? Sure, we should probably do 2 more scenarios real quick. I mean, there's the scenario where there's 0 acceleration and then the speed remains constant. But let's just, for the sake of argument, have Vx of t going to the left at that moment, and then let's just put acceleration in the same direction. Okay, well, in that case, we know that the speed Vx is going to increase. Right? It increases because velocity and acceleration point in the same direction. Now it decreases, meaning the object to point mass is going to move faster and faster to the left. Okay, and here you can have the scenario where you slow down. So you're moving to the left, but really you're slowing down because the acceleration points to the right. And it's a little tricky to talk about acceleration right now because we don't really know where it comes from. We don't have a way to say, oh, well, this is acceleration because this and that, or because these are the forces acting on the object. We don't know what forces are. So here the speed Vx decreases. Okay, so it'll make more sense once we have Newton's second law where acceleration comes from. What you'll find is that for now, very often you're going to be given the acceleration straight up, or you will be put in a situation where you're supposed to know what the acceleration is, basically. Okay, so we talked about position, talked about velocity and acceleration. Position is where you are, velocity is how fast your position changes, and then acceleration is how fast your velocity changes as your position changes at the same time. Okay, so it's important to know these properties, and it's important to know how these quantities are related. Let's just do a little bit of a summary here and organize this content a little bit differently so that we know what to expect. And I'm going to start this summary with, I wouldn't say a disclaimer, but an important thing to keep in mind, an important note, which is that in Physics 8a, acceleration ax of t is constant. Now, acceleration has no reason to be constant in the real world. Probably isn't. But we should learn to walk before we run. And so we're going to learn about motion with constant acceleration, which will therefore not be a function of time anymore. And we will say, well, yes, we could study motion with acceleration that changes, but all that would do is complicate the math, and it would not improve our understanding of kinematics and how these quantities are related. Plus, there's plenty of problems that we can do with constant acceleration that we don't need to go, change things up and make up problems where acceleration isn't constant. So we will purely focus on problems where acceleration is constant, with the exception, we'll talk about oscillations at the very end of the course, and then that will be the exception. But all the way up to that point, acceleration is going to be constant. And if it is, then we have the following. So let me just summarize in a different format what we talked about above. We're going to have position, that is going to be x of t along the x-axis. Then we have velocity, which is going to be Vx of t. It could be positive or negative depending on the direction of motion. And then we have acceleration. Okay, now acceleration, I'm going to write a sub x. I'm not going to write it a sub x of t because I'm just said acceleration is constant in Physics 8a. So I'm just going to call it a sub x. It's not a function of time. And I know that to get from position to velocity, I have to take the derivative. Okay, I have to take d dt of position, that gives me velocity. And then I have to take d dt of vx, the velocity, to get acceleration. Which means, of course, that if I want to go the other way, I'd have to integrate the acceleration with respect to time to get velocity, and I would have to integrate the velocity with respect to time to get position. And if acceleration a sub x is constant, well then the antiderivative is going to be a sub x times t plus a constant of integration. The constant of integration is going to be v naught x. That's going to be the initial velocity in the x direction. Okay, so this is the initial velocity along x. And then I can take that and I can integrate it again to get x of t. Well, ax t is going to integrate into 1/2 ax t squared, because the antiderivative of t is t squared over 2, plus v naught x is a constant, it's just a number, so it integrates to v naught xt, plus some constant of integration, which ends up being x naught, the initial position of my object when the problem begins. Okay, so these are the kinematic equations that we're going to be using. And it's really important to know what they look like. It's important to know this, and it's important to know this. Those are going to be our kinematic equations, and they're valid as long as the acceleration is constant. If the acceleration ceases to be constant, we cannot use these formulas anymore. But for 98, 99 even % of the time in Physics 8a, we were going to have constant acceleration. It'll only change when we get to oscillations. So that's important to keep in mind. That's how everything is related. And if you wanted to take away the important formulas of this week, it would be 1/2 ax t squared plus v naught xt plus x naught, and then vx of t, which is the derivative of x, is going to be axt plus v naught x. I'm going to put a curly brace next to these two because they go together, right? This one is the derivative of this one, so they kind of go together. And then there's a third one that is quite useful, and we're going to talk about it when we do practice problems. It's going to be v final x squared is v naught x squared plus 2 a sub x delta x. And so those are going to be the formulas that matter, and we're going to do problems to see how you apply them. Now, you will find that invariably in lecture, other formulas that are part of kinematics are derived. And fair enough, v initial plus v final over 2 times time is going to be your displacement, things like that. Those are all true. I don't have a problem with them. They're nice to have, but this solves any kinematics problem, so these are really the core equations that you need. If you happen to memorize the other ones that show up, now and then they're faster, but they're not necessary. This is what you need to solve any kinematics problem. And so now let's dive into a kinematic problem and see how you would solve it and set it up. So we'll actually start with free fall because it's an important concept to know about. We have a ball that falls from rest from a height h is equal to 100 meters and bounces off the ground. How long does it take for the ball to hit the ground, and what's the velocity when it hits the ground? And FYI, y is positive upward. So that is the direction along which we have motion. This week we're only doing one-dimensional kinematics, so you only move in one direction, vertically, and you can choose up as positive or down as positive. You can do what you want. Well, I chose up as positive. I imposed that for this problem. And what we're going to do is we're going to set up our kinematic equations, and we are going to then figure out the time it takes for the ball to hit the ground and the velocity of the ball when it does hit the ground. Okay, so before we do that, we need to talk about this thing here, which is the acceleration due to gravity. Okay? Because of the gravitational pull of the Earth, which when you can't see it, you can feel it, of course. It's what pulls you down, back to the ground. If you jump up in the air and you fall back down to the ground, it's gravity's pulling you down. So gravity's there, you can't see it, but you can experience it. So in a sense, you do know what it is. But everywhere in the space surrounding Earth, or the surface of the Earth, there's this acceleration due to gravity, g. Right? Now, g is what we call the acceleration due to gravity. And everywhere above the surface of the Earth, we have gravity pointing straight down, now technically toward the center of the Earth, but basically pointing straight down perpendicular to the ground. That's where gravity's at. And so it exists, and it is an acceleration. It's kind of the weirdest thing. You're like, magically there's an acceleration. It comes from the gravitational force, which we'll figure out later, but there's this acceleration in the air, and what it means is that any object that just falls on its own in the air or through the atmosphere is going to have an acceleration equal to g, which in magnitude, g is 9.8 meters per second squared. Okay? And so this is going to be the acceleration of any mass m falling through the atmosphere will have an acceleration equal to g in magnitude. Okay, and again, we don't have the tools yet to really understand where it comes from or to derive it for a given problem. We will once we learn about Newton's laws and about gravitation. But the point is, by virtue of having an object falling through the atmosphere, you communicate to it an acceleration equal to g directed straight down toward the ground. That's just how it is. Now, be careful that I said a mass falling through the atmosphere. I did not say a rocket, being thrusted through the air, or someone falling through the air with a parachute or anything like that. You can't go do that kind of stuff. If you introduce, and again, we don't know what forces are, but if you introduce other forces like air resistance or the force from the parachute or the force from the rocket thruster, things like that, this is no longer true. But what we call free fall is a mass either falling through the air or even being thrown through the air, as long as you neglect air resistance, because it will be free falling, meaning that it will only be experiencing this acceleration due to gravity. Okay, so I say this because, again, for this chapter and the next, we're just going to accept on faith that there's an acceleration downward that's equal to gravity, but we're not going to try to explain it or argue where it comes from or how we would know. We're just that's just something on faith that we'll accept, that we have to keep in mind, though. Okay, so we have motion down toward the ground, which is in the minus y direction, and we are trying to figure out how long it takes to hit the ground and the velocity of the ball when it hits the ground. Okay, so the first thing to do is to write the kinematic equations.
Okay, now of course the first thing to do is to realize that this is kinematics, which this week is pretty easy, that's all we know. But in the future, you want to recognize when kinematics are a part of the problem, and so then you can write the equations. Now let's write the equations. If we remember, and let me just scroll up real quick. If we remember this was for the x direction. Well, I can write the exact same thing. It's just that instead of x, I'll write y, and it'll account for motion in the y direction. Okay, so I'm going to rewrite these in the y direction. And what does it look like? It's going to look like this. It's going to be y of t is going to be 1/2 ay t squared plus v naught y t plus y naught. And then vy of t, which goes with it, is going to be ay t plus v naught y. When you are solving a kinematics problem, you are looking for three things. You need to know acceleration, initial velocity, initial position. If you know these three things, then you have your kinematic equations. Okay, now acceleration, well, in this case, it's gravity. We just accept it. But in general, you could find it with Newton's second law. We'll learn about that in a couple weeks. V naught y is the initial velocity. Here, the ball falls from rest, meaning that v naught y is going to be 0. And then y naught is the initial position. Okay, now if I say that y is equal to 0 at ground level, right, then the initial position of the ball is capital H. Okay, so I'm going to have ay, the acceleration, is g in magnitude. However, up is positive and g points down. So this is minus g. V naught y is going to be 0 because the ball is initially at rest. And then y naught is going to be the initial position. It's going to be h. Okay. And this is typically something that you derive, or you just claim that it's gravity in case of free fall. This is typically given, right? It's the initial condition for velocity, so you're either initially at rest or not. And this is up to you in the sense that it is up to you where you place y equals to 0. But I tend to like placing y equals 0 on the ground and then making y positive up, because that is how we measure height in everyday life. It's an intuitive way of measuring height, so I tend to do that. But you could say that y is equal to 0 here, and you could make y positive down and a whole bunch of other stuff, but in general, that's up to you. Okay, and in this case, it wasn't even up to you because I imposed this so that we could talk about this minus sign here that you can't forget. Okay, so I have my kinematic equations, yeah? Because now I know these three things that I highlighted. I know acceleration, initial velocity, and initial position. And so y of t is going to be minus 1/2 g t squared, well, plus v naught y is 0, so that goes away, and then plus h. And then this is going to be minus gt, and then plus 0 because v naught y is 0. So these are my kinematic equations, and they're going to give me the position and the velocity of the ball as it falls from rest. And that's a good thing because I actually want to know about its position and its velocity. Hitting the ground is a statement about its position. And then I want to find its velocity when it hits the ground, so obviously that's a statement about velocity. And so what I've done here is I've written these equations, and this is the hardest part of physics. Everything that comes after this is pretty straightforward and pretty mechanical. But taking the information that you're given and writing this, meaning not only do you know that you have to write it, but you're able to write it correctly, that is the art of setting up physics problems. And it's very hard to do at first because it's just not how other classes work. Even in math you're given a function and you're told to find the first and second derivatives and then the tangent or whatever. But you're given the function.
It's already there. You don't have to come up with it. In physics, you have to come up with this. And this is the hard part of the problem. So this is what you want to spend time on and become good at. And I say that because you'll find pre-med students, and this is not a knock on you because you are my favorite students. Pre-med students, you make two mistakes when you study physics. You study the problems that you know how to do because it makes you feel good about yourself. And then you look at the solution too quickly. Okay? Meaning that the whole point of the problem is to get to this, because everything else that follows you'll see is mechanical. But getting to this is the hard part. And if you skip the hard part because you're stuck, you don't know, so you quickly look at the answer and you see this, and you're like, yeah, I get it. And then you go and solve. Well, you're solving the not important part, the mechanical part, the part that's not hard to get good at. Okay? Because the whole point was to get to these guys from the problem and knowing that this is what you have to write and then writing it properly. So I've said it once, I'll say it again because it's the biggest issue with physics, especially if you've never taken physics before. The only thing you want to do is write things that are true about the problem and are relevant. And this is true, and this is true, and it's relevant because it's going to describe the motion of the ball as it falls. So then can I find how long it takes for the ball to hit the ground? Okay, probably can. Let's say that this is t is equal to 0. The problem begins when the ball is released, and the ball is going to fall down and hit the ground here. And it's going to hit the ground at a time t final. I don't know what it is, but that's what I'm solving for, right? And so the question now is, based on these formulas, these kinematic equations, how do I describe the fact that the ball hits the ground at t equals 0? T equals t final, sorry. It starts off at t equals 0 up here at rest, and it is dropped, and then it reaches the ground at time t final. And I want to find what t final is, okay? And so I have to say something that's true at time t final. And it has to be a statement either about position or velocity. Okay. Well, when t is t final, so at time t final, we have the following. We have y of t final has to be 0. It has to be the case that the ball has reached y equals 0 at time t final. I cannot make a statement about its velocity because whatever its velocity is, I mean, other than to say that it's downward, it's going to be Vy of that time t final. Now, if I know t final, I can then plug it into here and I'll get velocity, cool. But right now I don't know t final, is what I'm solving for, and so I can't say anything about this that would help me find t final. But this is enough, okay? If y of t final is equal to 0, then I can solve the following. I can solve y of t final is equal to 0, which means that minus 1/2 of g t final squared plus h is 0, okay? Y of t final is this for t equals t final. So that's 0. Okay, so then 1/2 g t final squared has to be equal to h. We're going to multiply by 2, divide by g, and then square root. It's going to be 2h divided by g, square root. Now careful, this is a very common mistake in physics, and it goes unnoticed for a while because a lot of the quantities we solve for are positive. But the reality is that mathematically, we should write plus or minus. However, time is always positive, and so typically we don't bother, okay? But what we should do is this. We say keep positive root because t final is positive. Okay, that's really what we should do. And so then we would say, okay, well, of the two options, plus or minus, it's going to be square root of 2h over g. Now, of course, when it comes to time,
you're always going to be keeping the positive root because time is always going to be positive. But if you're solving for a quantity that could be negative, you might want to entertain the negative root, depending on the problem. Okay, so then what is this? Well, the square root of 2h over g. In this problem, I actually know what h is, and I know what g is anyway, so it's 2 times 100 divided by 9.8, and that is going to be approximately equal to 4.51 seconds. Okay, so I actually had numerical values to plug in here, which will typically be the case for homework problems, although some homework problems are variable only. Exams have moved towards variables only in 8A in the last few years. Some professors did numbers, some professors did variables, and it wasn't, I mean, you could argue for one or the other, but it tends to kind of uniformly be all variables at this point. What that means is that I know you hate this and that you would rather plug in numbers off the bat, but the faster you become comfortable with an all variables solution, the better, because more likely than not, that's what you're going to be asked to produce. So I know that it's very comforting to plug in 9.8 because then you can divide that by 2, and to plug in 100, and it's numbers, it's tangible, like we get it, like there's a value, and I don't like to solve with variables only, so I would rather plug in numbers because it means something to me. And that's all fine, and I get it, and it's true, but you will probably not have numerical values on the exam, and the best way to do physics is to do it this way. Okay, the reason is very simple, actually. That if you plug in numbers here, you are going to forget what they represent by the time you make it to here. Now you might say, well, I don't care, I just want the answer. That's fine. But the truth is, if the next question after this one is like, oh, well, we double h, what happens? Well, you know what? If we double h, I'll just write 2h, and I don't have to rederive everything, and I'm done. So that's the power of variables, and that's why we use them, is that, first of all, it tells you directly that the time is a function of the height and gravity, fair enough, but it also then tells you what happens if you multiply the height by 2. How much more time is that? Well, I don't want to rederive the whole thing. That's silly. I just want to change height and then say, okay, that's the answer. So anyway, try to use variables only whenever you can. And here, okay, we could plug in some numerical values. We got 4.51 seconds, and that's the time it takes the ball to hit the ground, having fallen from rest. So, with that said, what's the velocity of the ball when it hits the ground? Okay, well, when it hits the ground, the velocity is Vy of t final, right? If you think about these kinematic equations that we have here, what they're telling you is that if you tell me time, I will give you position and velocity, right? So from the moment I know time, I know everything. I know where I am, and I know how fast I'm moving. So if I know t final, all I have to do is plug it into here to get the velocity at that time, which is what we want to know, okay? So the ball is going to hit the ground with the velocity Vy of t final. So the ball hits the ground with a velocity Vy of t final, which is, now Vy is minus gt, so Vy of t final is minus gt final. That's minus 9.8 multiplied by 4.51, and that's going to be approximately equal to minus 44.3 meters per second. Okay? And so then we can box that. Now, I will say, in addition to being comfortable with solving with variables, you should explain what you're doing to a degree, right? So you don't have to write a novel, but I said, hey, at time t final, y is 0. And then I solved that for t final. Okay. So that means that whoever's grading me can grade my exam without putting down their latte. which is precisely what you want. It sounds aggravating to hear that, that they would be so lazy to not put down their latte, but just it's an image, obviously. You don't want the grader to have to strain their brain or their eyesight to understand what the heck you're doing. Okay. I know that flies most of the time, especially if you have American GSIs. You have foreigners that are GSIs, and that shit doesn't fly. Because in their country, if you can't read it and if you don't explain what you're doing, guess what? You get 0 credit. Not partial credit, not, some, we get it, like, you meant to do it, you didn't do it. No, no, no. You just get 0 credit. Like, that's it. So, keep it in mind, you have to show your work in physics. The only way you can show your work is by writing what you're doing. That means equations, but it also means stuff like this. Hey, the ball hits the ground with a velocity. I should probably even add equal to be honest, so that the sentence makes sense in the first place. Equal to, Vy of t final. Okay, I get it. Computing velocity like this, we know t final, get a number, don't forget units. An answer without any units doesn't make any sense. And box your answer so that it's easy to follow, right? And you will see, I promise you, for 2, you can imagine an exam presented like this and the exact same information on another exam presented all over the place, half erased, poorly boxed or not boxed at all, complete chicken scratch. I promise you the former will get more points than the latter. And the grader might not even do it on purpose. It's subconscious. Like this will be much more forgiving if you make an error here, you miss a minus sign or something, than if it's complete chicken scratch. So anyway, that was a very long solution to a very short problem, and I get that. But there was a lot of things I wanted to touch on, and it was the first problem we were doing. Now we're going to go a little bit faster as we go through the second problem, but there was a lot of things I wanted to bring up and to talk about, so that's why it took so long. But as a general rule, when it comes to kinematics, these are your equations because you have constant acceleration, and you will write down these equations. You have to find the 3 quantities: acceleration, initial velocity, initial position, and then you can solve any question that is thrown at you. So let's have a look at a different problem. This is an old exam question, actually. I think it was a Golightly exam from a while ago. It's a classic anyway, one way or another. Whether this exact problem or some variation of it, it's the same thing. Now this one is a pure variables problem. There are no numerical values, so we're going to practice variables. We're also going to practice drawing out what's going on and then setting up equations. So we have a rocket that rises vertically from rest with an upward constant acceleration ay until it runs out of fuel at a height h. After this point, the acceleration is that due to gravity alone. And we want the speed when it runs out of fuel, how long does it take to run out of fuel, and the maximum height that the rocket reaches. Okay, so before we even start, remember that I said in this chapter we don't know where acceleration comes from. We don't have any tools to compute acceleration because we don't know about Newton's second law yet. So somebody has to tell me what acceleration is. And that's exactly what the problem is doing. Is that for the first phase of motion, there's this upward acceleration ay that comes from probably, the thruster on the rocket or whatever. But somebody has to tell me that. And then after that, after you run out of fuel, it's just gravity. Okay? So this is a problem where there's 2 different phases of motion. A first phase with an upward acceleration, and then a second phase where it's a downward acceleration, which is just gravity. That's it. Okay, but again, I don't have any tools to figure out acceleration, so I have to be given enough information to know what's going on. And let's maybe draw this out real quick. This is going to be the rocket, and the rocket is going to start at rest on the ground. Now, probably I would choose y to be positive upward. That's just tends to be my preference. And I would probably set y equals 0 on the ground. And then this rocket is going to reach a certain height when it runs out of fuel. Okay, so we're going to make it to a certain height here where fuel runs out. Okay, now the thing is, it is not true that at that point, the moment the fuel runs out, that the rocket starts to fall. Because at this point, the rocket has a certain amount of velocity, right? It's been accelerating upward, so it has a velocity. Perhaps I'll call it v1, and perhaps I'll move this down so I have enough room to draw the rest. So it's still moving up. So it's going to take a little bit of time for gravity to slow this thing down to a stop, right? And it's going to reach a max height somewhere here, and at that point, v2 is going to be 0. Now that was the tricky part of this problem. A lot of students got that wrong or didn't see that. They just thought that from here on out, it just fell immediately. Right, well, v1 is going to decrease because of gravity, and when it hits 0, that's your turnaround point. Right, a velocity of 0 means you're no longer moving up, but you're not yet moving down. Right, you're just suspended in air at that moment, and after that you begin to fall immediately. Okay, so we want to find the speed of the rocket when it runs out of fuel. Turns out that's v1. I gave it that name, but it's v1. How long does it take to run out of fuel? I don't know, but maybe I'll call the time t1 just to be consistent. And then what's the maximum height? Okay, well, let's call this time t2. I don't know if I'll need it, but I'll introduce it. And then y here is going to be, I'm going to call this h1. And this is going to be h2. Now, both of them measured relative to the ground. Okay, so in other words, this here is a change in height, h2 minus h1. Okay, and because I have two different phases of motion, one where the acceleration is equal to, just call it ay, the other where the acceleration is going to be now minus g, right, because g points down, right, and up is positive. But I have motion that has two separate phases. A first phase with an upward acceleration plus ay, a second phase with a downward acceleration g, which means the acceleration is minus g. I need to make sure that I set up kinematic equations for this first phase, but then I'm going to have to set them up again for this phase. I have a new set of equations for the second phase of motion. Okay, so that's something to keep in mind, is you can't have just y of t and vy of t for the whole thing. From here to here, it's not going to work, because in between, the initial and the final, there's a change in acceleration. Okay. Now, if I want to find the speed of the rocket at the instant it runs out of fuel, I can say I want to find v1, so I only care about the kinematic equations for this first part here. Okay, so what are my kinematic equations? My kinematic equations with a constant acceleration are the same equations that we wrote earlier, right? It's the same standard form. It's y of t is equal to 1/2 ay t squared plus v naught y t plus y naught, and vy of t, which is the derivative of the above, is ayt plus v naught y. Okay? Now, what is ay? Well, actually, ay is ay, so that's convenient. Okay, so I know this, cool. V naught y is going to be 0 because the rocket starts at rest, and y0 is actually going to be 0 because the rocket starts on the ground, and the ground is y equals 0. So my kinematic equations are going to simplify quite a bit. It's just going to be 1/2, well, ay, that's just what they call the acceleration, t squared, and then this is going to, of course, be 0, and so this is just ay t. Okay? And those are my equations. That's the hard part, is setting up the problem. Now, what I have to do is write things that are true that are going to allow me to solve for v1. Okay, given that I don't know what h1 is for that matter, right? So if I go back and I look at this, I just want the speed of the rocket when it runs out of fuel. Actually, I'm sorry, I said I didn't know h1, but I do. This is this is why you have to read the whole thing and you can write down the knowns, by the way, right? So h1 is actually equal to h. So I take that back. My apologies, I spoke too quickly. Here I know what h is, okay? So I can figure out what v1 is probably, because there's only going to be a certain, well, for a certain height h, there's only going to be one speed v1 that the rocket was able to achieve in that amount of time. So there's two solutions, or two ways of doing it. So solution number one, or method number one, if you want to call it that, we're going to say the following. We're going to say that at time t1, we have the following. And we're interested in time t1 because that's when the speed is v1, right? So at time t1, what is true? Y at time t1 has to be equal to h, which is known. But also, vy of t1 has to equal the speed v1 that I'm looking for. Okay? So these two things have to be true. And that means that I need to have 1/2 ay t1 squared is equal to h. Okay, y of t1 is this when t equals t1, so it's this. And then vy of t1 is just ay t1 is equal to v1. But these two things are true for sure at time t1. Now, what do I not know? I don't know t1, and I don't know v1. But I have two equations for two unknowns, and in math, one equation will allow me to solve for one unknown. What that means is that I have enough equations. I don't need more equations. However, of the two equations, probably easier to solve the first one to get t1, because like that, when I have t1, I can find v1. So even though I don't actually care about t1 in the first place, I need to solve for it so that I get v1. Okay, so let's solve that. Let's solve 1/2 ay t1 squared is equal to h. Okay, we're going to multiply by 2, divide by ay, and we're then going to square root and keep only the positive root because we're solving for time. Okay, so t1 is equal to this. And nobody asked me to solve for t1 here, but I did, and it's an important intermediate result, so I'm going to circle it or box it. And then, okay, then I can say, well, I'll solve ay t1 is equal to v1, and I want v1. Okay, so v1 is ay times t1, which is square root of 2h over ay, which, by the way, that is square root of 2 ayh. Okay, just to be clear. Okay. I know somebody's going to ask, so let's just do this. Square root of b multiplied by, shoot, no, I can't even do it right, my bad. Square root of b, no, 1, 2, 3, wow. b times square root of c over b is equal to, well, if you absorb b under the square root, really upstairs you're going to get b squared times c over b, and that cancels that, and so that's how you get square root of bc. Okay. If you're not comfortable with roots, exponents, things like that, do yourself a favor, go get some worksheets online for free and bang out, I don't know, 25 worksheets of exponents and natural logs and exponentials and the kind of stuff that if you haven't done in a while you forget. You will thank yourself for it later. You can even thank me if you want, but at the very least, you will thank yourself for putting in the effort, because this is the kind of stuff that you don't want to get stumped on. So v1 is square root of 2ayh. All right. Now, how do we do that? Just a quick recap. We set up our kinematic equations. We found acceleration, initial velocity, initial position. It's like, okay, cool. And then we said, well, at time t1, these two things have to be true. And a very classic move in kinematics is to first solve for time, even though you might not care. And then you get what you want by plugging time into the other equation. It's very classic to do that, two-step solving technique. So that's the first way to do it. That's solution 1. Okay, what is solution 2? Okay, well, let's go over solution 2 because it's going to let us use the third equation that we haven't used yet. And we have boxed up on the first page. So let me do this. I'm going to make a copy of this. I'm going to shrink it just so that we have it here. Okay. Maybe not too small that we can't see it, but there we go. And I'm going to use the kinematic equation v final y squared is equal to v naught y squared plus 2ay delta y. Okay, now this is a very different equation than these equations, right? These equations are functions of time. Time is the input, you get an output, which is position or velocity. Here, this is not a function, right? There's no input. It's a relationship between quantities. And you apply it between an initial location and a final location. And that's up to you. It doesn't have to be the beginning and the end of the problem. It's choose an initial moment, choose a final moment, and write down this thing in between those two moments, right? And so this is not a function. There's not even time in it. It bypasses time completely. But that's a good thing because, like I said, we don't care about T1. At first, all we want to find is V1. Nobody asks us about T1. So I'm going to apply this between the following 2 points. I'm going to apply it between this location here, where I know how fast I'm going, and this location here, where I want to know how fast I'm going. That's going to be my initial and my final. Okay, so then V final is really V1 squared is equal to V naught y squared, that's the initial velocity, but it's 0, plus 2. The acceleration ay happens to be called ay, so okay. And then delta y is my change in y. And my change in y is h minus, I started 0, so that's it. And I'm just going to square root this to get the speed, and I'll keep the positive root because speed is positive. And I'm going to get square root of 2ayh. Okay, so this kinematic equation bypasses time. It doesn't have you first solve for time like we did here, only to plug it into the second equation. In fact, whatever we did here is completely built into this third equation. That's where this equation comes from. If you, in general, isolate time, plug it back into position, you're going to get this guy. And you're going to say, okay, well, you've basically eliminated time and you've built a relationship that is going to give you speed if you know displacement and acceleration. And of course, initial speed. So that's a faster way to do it. And it gives us the answer to the first question, which is what is V1? Now, question 2 says, when does the rocket run out of fuel? Well, that's the time, right? So that's really T1. But we already found T1. T1 is this. Okay, so I'm going to take all of this, and I'm going to do this. And sometimes in physics, this is going to happen. You can have a question where what you're asked to solve for, you've already solved for. Okay, and so we're going to say the rocket runs out of fuel at time t1 equal to you just box the answer. You don't have to do the work again. You already did if you use solution 1, right? Now, what this means is that whoever wrote the exam was probably thinking solution 2 to find V1. They're like, oh, well, like that, they'll use that to find V1. And then I can add another question. I can say, oh, what's T1? Okay, and then they'll go solve for T1, which is fair. Okay, it's just that we went about it a different way. We said, well, okay, I'll solve for T1 first, even though I don't need it, because if I plug it back into here, I'll get V1. And then I do know T1. Even though nobody asked me to find it, it's still a relevant quantity for this problem. So why not? And then if you're asked to, solve for V1, and you already did, you say, hey, I already did. This is T1. And you're done. Okay. So then what is the maximum height that the rocket reaches? All right, let me, again, apologies for all the scrolling. Let me grab this, because this is a good summary of the problem at hand. Okay. And so question 3 wants us to find H2. Basically wants us to find H2. By the way, let's just remind ourselves, V1 is square root of 2 AY H. Okay, that's what we found earlier. It's going to matter because, like we said before, I have now a new phase of motion with a new acceleration, and so I need to set up kinematic equations for that new phase of motion. I can't just use the ones that I've been using. Right? The equations that I've been using effectively expired when the rocket reached this point, because then the acceleration changed. And that's really important to realize that. Okay? So let's rewrite our kinematic equations. And this is once the rocket runs out of fuel. Okay, so y of t, the standard form, because we have constant acceleration, is 1/2 ay t squared plus v naught y t plus y naught. I have to be careful. V naught y and y naught do not refer to this. They refer to the initial velocity and the initial position starting here. Okay. And then Vy of t is going to be just Ay t plus V naught y. Now I know what Ay is. Ay is minus g. And I know that V naught y is actually V1. That's how fast the rocket is moving at the beginning of this new phase of motion. And then y naught is actually h, because that's how high the rocket is at the beginning of this new phase of motion. So y of t is going to be equal to minus 1/2 ay t squared plus, well, I'll call it V1 for now, but V1 is equal to this, and I can plug that in later. Plus V1t plus h, and then Vy of t is minus gt plus V1. Okay. So, with that in mind, can I solve for H2? H2 is what I want. I don't know T2, but I could probably solve for it, and if I did, then I could plug it into here, and y of T2 ought to be H2, I think, because, by the way, y naught, I said, is h, meaning I'm still measuring with respect to the ground. So yeah, if I could plug in, T2 into y of t, that would give me H2. Okay. Now, careful, by the way, that, yeah, we found T1, but we're going to have to restart the clock here. Right? So this is going to be, we're going to set t equals 0 here. We'll restart the clock. We're just going to find T2. It's going to be a lot easier. And then if we wanted the total time, we would add T1 and T2 in the end. But the point is, for this new phase of motion, let's restart the clock at t equals 0. okay, as if it were a new problem in a sense. Okay, so how are we going to solve this? How are we going to solve for h2? Well, we can say that Vy has to be 0 at time t2, and that y has to be h2. So solution number one, we're going to do just like we did before, the classic two-step solving where we solve for t and then we actually use t to get what we want. So at time t2, we have the following. We have y at time t2 is going to be h2, which is what I want, and Vy at time t2 is going to be equal to 0 because at time t2 the rocket turns around. It's no longer moving up, it's not yet moving down, so it turns around. Okay, which means no velocity. Okay, so y of t2 is equal to h, and h2 I mean, and then Vy of t2 is equal to 0. Okay, so I suppose, let me do this. We have this. Okay, and I just want to make sure I have enough space. Okay, which means that we have this. What is y of t2? Well, it's this when t is equal to t2. So, and my bad, this is g obviously, duh. All right, ay is negative g, so careful, that thing, it should be g. Okay, so then y of t2 is this thing when t is equal to t2. So it's minus 1/2 g t2 squared plus v1 of t2 plus h, and that apparently is equal to h2. So if I only knew t2, I would be done. I would plug it into this and I would find h2. Okay, well, Vy of t2 is equal to 0 is minus g of t2 minus gt2 plus v1 is equal to 0. Okay, so what do I do? Well, I have one unknown here, t2, I don't know what that is, and it's also an unknown here, but I also don't know h2. So I'm going to use the second equation first, and I'm going to solve for t2. So I'm going to say minus g t2 plus v1 is equal to 0, leads to t2 is equal to v1 over g, which, by the way, is square root of 2ay h, that's v1, divided by g. Don't care what t2 is really, but hey, it's an important intermediate result because if I have t2, I can plug it in here and I can get the answer. In other words, I can find that h2 is equal to, now minus 1/2 g t2 squared is going to be 2ay h divided by g squared plus v1 times t2. Okay, well, v1 is square root of 2ay h multiplied by square root of 2ay h over g plus little h, which is known. Okay, so this is going to simplify. This 2 is going to go away. So this is going to be minus ayh plus over g. Shoot. Don't forget g. There we go. Plus 2ay h divided by g plus h, and that's just going to be ay over g times h plus h, which you're welcome to leave as is, but you will find that a rule in physics is we tend to factor as much as humanly possible, and so you would typically find it presented in this form. There we go. And that's going to be h2. Okay, now if we go back and we have a quick look at what we did the same thing that in the first part, right? As in the first part. We did a two-step process for solving. First, we found time, even though we didn't care about it, and then we plugged it into another equation and we found what we wanted, which again is a very common way of solving kinematics. However, there's a different way to do things in this case. Let me make a copy of this. And you already know what the other way of doing it is, right? Based on what we did before. And you might actually just choose to do that. I mean, it's a lot easier than doing the first method that I did here. So solution number 2, or method number 2, whatever you want to call it, is going to be, well, let's use v final y squared plus v naught y squared is equal, to v naught y squared plus 2ay delta y. Now let's apply it between here and here, because that's now the initial and the final for this second phase of motion. So what that means is that v final y is v2, square that, and that's going to be 0 anyway, is equal to v naught y is, careful, it's v1, right? It's the initial velocity in the y direction, but starting here, plus 2, your acceleration is now negative g, we're told, and delta y is h2 minus h, that's the change in height, okay? And so we're going to find that 0 is equal to v1 squared, well, by the way, that's 2ayh, because v1 is square root of 2ayh, minus 2g h2 minus h. Okay, so that's going to give me, now 2 is going to go away, I can cancel that. That's going to give me g h2 minus h is ayh. Got to divide by g. I'm going to get h2 minus h is going to be ay over g times h, which of course eventually gets me the same answer as I got above, h plus ay over g times h, and that is 1 plus ay over g times h. Okay. Again, a little easier because this method has built into it the solving for t and then plugging it to the other equation. That's how this equation comes about. So a lot easier to just do that if you don't care about time, right? If time is irrelevant, meaning that nobody asks you to find t2, we just wanted you to find h2, and you knew speed here, initial height and acceleration, well, yeah, t2 is a certain amount of time. It is, whatever it is, it's a fixed number, and there's only one value of t2 for h2. That's true. But if you don't need it, then it's faster to do this. Now, if the problem is going to say, well, hey, how long does it take to reach the max height, and then what is the max height? Well, then you might as well do this, right? Because you're first going to find t2, and then you're going to go find the max height because you know t2. So there's no reason to prefer one over the other in general. It's just, it's contextual. Right? It depends on the problem. So you have to see what you're given and what you're trying to solve for. And the truth is that with enough practice, it'll become obvious which one you want to pick. But anyway, that kind of wraps up what I wanted to talk about today. And if we just do a very quick recap of all of this, what I wanted to say is the goal of these live streams is just to really touch on the important topics every week. So it's not a lecture. Make sure you go to lecture and you have lecture notes to supplement all of this. This should actually supplement your lecture notes, really, is what's going on. But I wanted to talk about kinematics in one direction. That's position, velocity, and acceleration. And we talked about those. And we saw how they're related, right? Velocity is the derivative of position. Acceleration is the derivative of velocity. And because of that, under the assumption that acceleration is constant, we get these kinematic equations here that are going to be the kinematic equations that we use throughout the course. And then we did two problems, one which was just free fall, and we set up equations and we talked about the acceleration due to gravity so that we know what that is. And then we did another, which was a bit more complicated because this one had two phases of motion. It had a first phase here, and we needed kinematic equations for that, and then a second phase here, and we needed a new set of kinematic equations for that. And so it's certainly a harder problem than the first, but it's a more interesting one, and it's definitely exam level. So I would make sure that I understand how to set this up. And you really have to sit with this stuff and practice. So whatever you do for 8A, it's, 8A is like push-ups. You can't read about push-ups. You have to do them. Well, 8A, you have to do the physics problems, right? And it's a chicken and the egg problem because you're going to start, you're going to look at a problem, you're not going to know what to write. And maybe you'll write a few things, but not a lot, and you'll get it wrong. But it's okay. Do that. Go as far as you can in terms of writing things. And then look at the solution. At some point, you have to look at the solution. And understand what you missed and why you missed it, or what you did wrong and why you did it wrong. It's going to take a lot of time, and it's going to seem like it's not productive, but is in fact very productive. Because if you do that 2, 3, 4 times, then you have a toolkit of 2, 3, 4 problems that you can kind of dip into. Because then when problem 5, 6, 7 come around, you're going to see that some of those questions are very close, if not similar and identical to the previous questions that you've answered. There's only so many questions we can ask. So you're trying to build your toolkit, but it's iterative, right? The first problems are going to suck. They're going to take a long time. Make sure you understand the solutions and why everything is done the way it's done. And then keep doing some more, and you will see that you will improve over time. But it takes a lot more time than getting good at Bio 1A or Chem 3B, right? It's not a volume problem. It's really it's understanding each problem as you go, and the more you do that, the faster you conquer these concepts and you get more comfortable solving problems. And of course, that's true for each chapter, but there's a certain way of thinking and setting things up in physics that you're gonna that's gonna build over the entire course, and just by doing physics, it's gonna help. But yes, in any given chapter, you're gonna have to kind of go over that hump initially of, I don't know where to start, and then, oh, okay, I've done a few, I kind of know where to start. It looks like this previous problem. But the point is, you have to do the problems. You cannot just read about them. You have to put pen to paper and kind of bang your head against the wall. And if you get stuck, that's the best thing that can happen to you, because it will tell you what you don't really know. It's frustrating, and I get it, and it seems like a waste of time, but I promise you it's worth it. So do a lot of problems. Make sure you do problems that have solutions. Do not do problems without solutions. That's a waste of time, because you're never going to know what's wrong. So you need to find problems with solutions. Make sure that you do that. The study guides are a great resource, not to toot my own horn. If you want more help than that, in addition to the study guide, if you want individual help, the master classes are also a great resource, since you get access to me unlimited for the semester. So there's other options. Obviously, you can try the SLC. If discussion is enough, don't bother. If you have a book that you bought on Amazon and you prefer that, do that. But whatever you do practice problems with solutions, because that is the best way to get good at physics. And with all of that, thanks for watching. Let me know if you have any comments or questions. I'll try to answer the interesting questions that I get at the beginning of each live stream. This is the first one, so nothing yet, but I usually get some questions coming through, and some of them are worth discussing. So I'll do that at the beginning of each live stream. Feel free to contact me if you want to chime in or ask anything, and have a great week. I will see you next week. Take care.